Hi there, and welcome to Artful Design TV. And this is Wang, and with me is Kung-Woo Kim.
Hello.
And today, in this coding tutorial, we will create a basic interactive audio visualizer using Unity. There are many ways to do this, and today we'll just show you but one way to get a basic visualizer going, something that you can then customize from then on out. So, shall we begin?
Yes, let's do it.
So the first thing we're going to do is to create a new project in Unity. So in this case, for this one, we're going to use a universal render pipeline project. You could easily use a 3D project if you like. And for this one, let's call it HelloAudioVisualizer. And as this is creating, we're going to outline the basic steps we are going to take in this coding tutorial. So we're creating the Unity project. After this, the first thing I'm going to do is to set up a real-time audio input, so we can actually get audio data from Unity and through Unity basically get at the microphone and other audio sources that you actually want to visualize. And then we're going to draw two things. One is the time domain audio waveform. And the second thing is a frequency display. That's basically a frequency analyzer showing you some things about the frequency content of the signal. You do not need a lot of experience with Unity or with audio. It would help if you've had some basic Unity experience, and we recommend taking the first rollerball tutorial if you haven't done so already with Unity. And that really should be all you need. And we'll explain the rest as we go. All right, so everything's loaded, and what we see here is basically just the sample scene that comes with the default URP project. So, all right, Kung-Woo, what do we do next?
So let's create a new scene for our visualizer.
And how do we do that?
So inside your assets folder, you go to your scenes folder, right-click on the folder, and create.
And scene. All right, now we have a new scene, and we're going to call this our audio visualizer. And so basically, we are going to leave all the other default assets kind of where they are. We're just going to basically leave them there, ignore them, and really not use them in this. Feel free to delete them if you like, but they really won't hurt anything if we leave them in there. All right, this is our new scene. And from here, what's our next step?
So should we create an audio source object first?
Basically as a game object?
So you can create an empty game object by right-clicking on the hierarchy tab.
And just go to create empty. And we now have a empty game object. And should we what should we call this? How about our audio source?
Yeah.
So this would be the kind of game object representation in Unity that's going to represent our that's going to be the instantiation of this audio input that we're gonna do.
And audio source needs an audio source component. So in your inspector tab, I would click on add component, and then add audio source.
There it goes. So.
Yep. And should we go right into scripting for the audio input?
Sounds good. So I'm guessing next we're going to go to scripts here.
Yep.
And then we're going to do a create, and we're going to create a new C# script. And we're basically going to write some code that initializes the audio and start getting audio piping into our project here. So let's call this audio input.
Yeah.
Okay. And it's going to go ahead and open this up. All right, so this is basically the general default C# script you would see, and we basically have these two functions that we are going to be using. So let's go ahead and populate start and update, right? So as a reminder, start is basically the function that is called once, right, before the very first frame is drawn in Unity. And then once per frame, once per video frame that is drawn, update would be invoked. So we want to think about really putting both the initialization of the audio input and then kind of any ongoing actions into update. So for start, what are we going to do?
We'll create a variable for the component audio source on top of the start function.
So call it the audio source, and then public audio source, audio source, and audio source. And you can have whatever convention you want. In fact, I'm gonna call it the audio source.
The audio source.
The audio source. And then we're gonna make so this is gonna be a reference to an audio source, and we're basically gonna get that reference from the game object that we just created. And we're gonna do this again in start, because we're gonna just do this once as an initialization. All right, so in this case, we're going to do the audio source equals get component audio source, and that should provide us the reference once we hook things up.
Yep.
So I guess next we will be setting up the microphone. And the way we're going to do that is we're going to go ahead and just show you the few lines it takes to do that. The first thing we're going to do is to make sure we actually have microphone devices. We'll do this as a sanity check. And so if microphone, and this is the kind of the standard class library microphone that comes with Unity, right?
Yes.
So we're going to do microphone.devices.length and make sure this is greater than 0, meaning you actually have at least one microphone audio device. And we're going to go ahead and get the device name, presumably of the default microphone on your system. For me, it should be this, for example, this microphone that I am speaking into. And so I'm going to do string selected device equals microphone dot devices 0. That's the first one. And we're going to do toString to get the string representation of that. Next, we're going to set the microphone as an audio clip for the audio source. This part, I have to tell you, doesn't make a lot of sense to me. As someone that's written a lot of audio code, but I think this is what works, so we're gonna go with it. And part of it is I don't fully understand the mechanics of this yet, but this is what this is actually what is recommended by Unity, so we're gonna go with that. So we're gonna do set microphone as an audio clip, and with my personal WTF, because I feel like the microphone is really not an audio clip, but it is what it is, I suppose, or it is what is not. The audio clip, audio source dot clip. We set that to microphone dot start. That's a function using the selected device, using the device name. True is basically saying we want this to loop. And so this one you can just choose any non-zero number. Right, so we're going to choose 1 for 1 second, and we're going to do something later to get the latency down from that 1 second, because actually 1 second of latency, if you were to speak in the microphone and hear your voice come back to you a second later, it would sound very delayed, and we want to really reduce that delay. And finally, we're going to use whatever the default sample rate audio settings. Am I doing this right? There we go. Output sample rate. Okay, so with this line, we've actually started the microphone, but also effectively connected that into as a clip into the audio source. The next line we're going to do is a bit hocus pocus, but this is the line that seems to be recommended to do if you want to reduce the latency, the time between the microphone picking up the sound and you actually hearing that sound come back as an audio output. And I'm just going to write the code. So I have a while loop.
Another WTF.
Yes, this is a couple of WTF moments in here, but it works, and it seems to be the recommended thing. So we're just gonna go with it. Microphone.getPosition using the same selected device, and as long as that's greater than 0, we're gonna do nothing. This makes no real sense to me at all whatsoever. What is this doing? Is it draining the sample buffer? I mean, WTF, this gets the official Kungwu and Ge WTF certificate here. But what this actually does in practice is that reduces input latency from the microphone. So this is the line that's actually quite important. Without this, you'll hear that big latency. All right, so I don't think we need to set the audio source to loop since we already put a 1 there, but that's for the microphone. So just for good measure, we're going to make sure to tell the audio source to loop. So with that, we're going to say the audio source dot loop equals true. So with that, that's basically our start. That's our start function, and this is the initialization to get the audio input initialized. Next, we are going to, actually there's one more thing we need to do here, and that is to play. So the audio source dot play. This should set everything into motion, and really, how could this not work? Just a bit of optimism we'll inject in here. So at this point, what we're really doing here is getting the audio back in the form of arrays of numbers. And these arrays of numbers account for just the digital values that is digital audio. So for example, in a second of digital audio, you might have upwards of 40,000 or more digital samples per second. And that's the digital representation of sound. And we're going to get just a small buffer, a small array of that, but we're going to do that very often. And that's what we're going to actually draw, are these digital values to represent the sound that's coming from the microphone. So for this, we're going to create 2 arrays of numbers. And each of these arrays of numbers are going to represent something about the audio signal that we're trying to draw. The first one is we're going to have an array that represents really just the waveform. This is actually the sound wave itself. You can think of this as the sampling of the air pressure fluctuating that results in the phenomenon that we call sound. And we're going to call this the time domain waveform. And for our purposes, we're going to just consider this to be mono, as just having one channel, not stereo. I'm going to do a public float array and call this, let's call this just the waveform. How's that?
Sure.
And it's going to be a new float. And should we go ahead and allocate a default value for this here? So we're going to just choose a nice power of 2, 1024. That's how many digital samples we will be they'll be held in this array. And that's the amount of audio data that we'll be dealing with, kind of, per frame, so to speak. And if you think about it, just for context, typically if we're running the system at like a normal audio rate, which might be like 44,100 samples per second or 48,000 hertz sample rate, this is quite a relatively small chunk of sound that's going to be in the tens of milliseconds, and that's kind of the unit that we'll be working with. And corresponding to the waveform, we actually want something to hold the frequency data. This is going to be a different representation of the sound, and this representation isn't really the time varying air pressure and or time varying values to represent the waveform. This is actually the frequency content of that same chunk of sound. I'm going to call this the magnitude spectrum. It's going to do public float and call this the spectrum mag. In fact, we're just going to call it the spectrum for short. And this is similarly another floating point array. And for this one, we're going to do precisely half of the size. And for reasons that we will get into a bit later. So for now, this is the data we have in here. As a reminder, we have the audio source, the reference to the audio source that's associated with the game object that's in Unity. We've connected the microphone up with this. Now we just created two arrays ready to be used to basically get data back from the audio source as numbers, so we can then use these numbers to do what we want, including draw them. So are we ready to do the update?
Yeah, let's fill in the arrays with the numbers.
Right, so this part is actually, by contrast, quite a bit shorter. So here, let's go ahead and get the time domain waveform. Basically, this is the sound wave. And we can do the audio source dot get output data. And we're going to send it the waveform. And we're going to tell it to do it off of the 0th channel, or really just the first channel here. And then similarly, we're going to get the magnitude spectrum from this as well. And this code is really just 2 lines because a lot of this functionality is already wrapped up in functions that's in the audio source. So it makes our job a little easier here. There are other versions of this where you might actually want to perform some of this analysis yourself, but we'll save that for a different tutorial. So this one is send it the spectrum, and this has basically still 0th channel. This is one extra parameter, which is an FFT window. This is a windowing function that is used to do the analysis, the fast Fourier transform, and the Fourier analysis that actually gives you the spectrum data from the waveform. So for this one, we're just going to use a fairly typical window, and if you don't know what this is, do not worry about it. But we just want something that is serviceable, and we'll use the good old Hanning window.
Yeah.
All right, and so Kung, I think this is all we need, if I'm not mistaken, for this particular class. The audio.
So
input.
let's see if we speak to our mics, it will pick up your voice as an audio clip and see if the float arrays are filled with time and frequency domain data.
Great. So I'm going to go back into Unity. Unity's going to do a little bit of thinking and contemplation. And do we need to hook anything else up before we go?
Yes, so we should drag and drop the script we wrote to the audio source game object.
Okay. So now if we do this, we actually see this.
If you click on the audio source game object, we'll see that the script is attached, and we can see the 2 game objects, the waveform and the spectrum. And right now it's at 0, but if we play and speak to it, it will probably change.
All right, let's do it. So I'm going to go ahead and say play. Check. Okay. So I am hearing my voice slightly delayed coming back at me. So all right.
That's a good sign. So can we check if the numbers change when you?
Yes, let's do that. So if we have this open, will these just change?
Yeah, when you play it.
So all right. So let's have this here. Check. And all So
All
that's
right.
a pretty handy way to actually debug this data.
Mm-hmm.
Cool. So we actually have our first step completed here, which is to actually have a game object with an audio source and to write a bit of code that sets up the microphone and attaches the audio source. And very importantly, we now have data in arrays, audio data in arrays that we can work with. So now what, Kongwu?
Now let's visualize this.
All right, sounds good. We are here to do an audio visualizer after all, and we're going to
Yes.
visualize.
Yes. So before that, let's have a cleaner environment.
Yep. Right now we have this nice looking skybox that we really don't need. So let's go ahead and get rid of it for this particular
Yes.
scene.
So in order to get rid of the skybox, you would go to Window
Okay, here.
and Rendering.
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 Where did it go?
Rendering.
There's rendering.
And lighting.
Lighting. Okay, then we have this thing that comes up.
Yep.
And for now,
And I
put
would
this here.
click on Environment
Okay.
and use change skybox material to none.
And
It's usually on top.
yep, there we go.
Yep. And should we have a black background?
Yeah, let's have just a pure dark background here.
Okay. That you can change in your main camera.
Okay, so are we done with the lighting here?
Yep, you can close it. So click on main camera and in the inspector, I would click on environment.
Let me see, where is it? Right here.
Yep. And background type to solid color and that to black.
Choose a solid color. Boom.
Mm-hmm. And this is different in 3D than in URP. So URP, you have to click on the environment tab and do the steps that Ge just did. But in 3D, you'll see the background color right away when you click on main camera.
Cool. So now we are ready, because right now if we were to play this, we actually don't see any graphics, but the sound should be coming back.
Yes,
Right.
it's the void.
It's the void. And
Right.
and our next step is really to draw this time domain waveform. We're going to draw the sound wave, so we can actually see the sound wave and have it respond to whatever is coming into the microphone. So you could, for example, draw a line that basically connects all the dots and plot it out in like this 2D way. What we're going to do here is we're actually going to kind of hack it with some 3D graphics. And we're going to draw a lot of cubes, and we're going to move the cubes into place. And we're going to have a lot of them so that drawn together, it kind of looks like a line. So with this, I believe our next step is to basically create a cube model, but also to do it in a way that we can encode, basically generate as many of them as we need. Right.
Mm-hmm.
So for this, we are going to create a cube prefab.
Mm-hmm. So I would click on the assets folder and create a new folder called prefabs. Yep. And in the hierarchy, 3D object and a cube.
Okay, so we have this cube.
And good practice is to, whenever you create a new game object, I would go to the inspector and next to the transform, there's those little 3 dots and I would click on reset. So that resets the transform into position 0, 0, 0, rotation 0, 0, 0, and scale 1, 1, 1.
Great.
So, yep, once that's settled, we can move the cube into the prefabs folder.
Okay, so I'm just going to drag it into there.
Mm-hmm. And once you have done that, you can erase the cube in the hierarchy.
Great. So now our cube is still here, but now it's basically as an asset, as a prefab. And what this is going to allow us to do is we're going to write some more code. In this code, we can dynamically instantiate not one, but as many of these cubes as we want. And rather than placing them one at a time into the scene, we're actually just going to programmatically do that. And this is important because we're going to need like hundreds of these to actually draw the waveform. All right, so let's do that.
All right.
Let's see. So at this point, I think it's time for us to actually create a new script that's going to do just what I said, which is to actually, this script will be responsible for drawing the waveform. So I'm going to do create, in assets, scripts, create new C# script. Let's call this waveform. And let's go ahead and open the waveform. All right, again, this is kind of the generated default structure for this. And once again, we're going to be making use of the start and update functions. So general plan for the waveform is in start, that's again the initialization. We're going to set up and basically instantiate all the cubes that we're going to be using. And we're going to set them into a state that they're going to be ready to be used. In an update, we're going to, as we get the audio data back from the microphone, we're going to use that data to move all these cubes basically into the right place so that they sketch out or plot out the waveform. So I think that's our general plan, right?
Yeah.
So to do this, where do we start?
So we should declare variables first. And I think the first variable we should declare is the prefab reference of the cube that we just created.
Great. So let's do a prefab public game object.
Game object.
And I'll call it, well, I think we're in the underscore.
The zone.
the V zone today.
The zone, yeah.
And then we're going to do array. And basically then, so this is the prefab, right? But what we really want is we actually want for every audio sample in our array. For example, we had 1,024 audio samples in our waveform array from the microphone. We actually want exactly one cube that represents each of those samples. And depending on the value of that sample, we're going to move the cube to a particular position. So for that, we're going to need an array of objects. So this is our array of game objects when used for that purpose. Public game object. And it's going to be called the objects. I suppose we could easily call this the cubes as well. Maybe that's clearer. Should we do that?
Sure, yeah, the cubes.
The cubes. And we're going to go ahead and just create, not the cubes yet, but the array to hold the cubes. And it's going to be 1,024. Keeping in mind, for now, we're just hard coding it, but this number is exactly the same as the size of the waveform array that we created in audio input. For brevity, we're going to hard code things, but as your projects grows, we definitely recommend some better conventions for not hard coding these things. But for now, just so we can get through this tutorial and show you how to get everything else hooked up, we're just going to do a little hard coding here. Great. So with this, what we'll need to do here is let's do some instantiation. So since we have a lot of things to instantiate, namely we have this many cubes, right? So we're going to go ahead and start a for loop, and we're going to basically go through this, and for each slot in the cubes array, we're gonna create a new cube and put it in there. So this is actually just going to be something like the cubes dot length, and that's the length of the array. And then over here, we are going to let's go ahead and instantiate away. And this just means make an instance, create an instance of this object. So we're going to instantiate a prefab game object. We're going to call it game object go for short, and we're going to use the instantiate function, and I'm going to pass it the prefab. This is super handy because once we have a prefab, we can create as many instances as we need. And this happens to be like a really useful thing a lot of times in designing things programmatically. So, whoops. So we do that once. The next things I guess we can do is go ahead and set it to some initial position. And so I think here we want to do a little bit of math and figure out what we want. For starters, we'll probably just want this thing as a horizontal line across the screen before we start modulating each of these cubes according to the sound wave. So what we're going to do here is to give it some initial position. And for this, we need to do a little bit of math. So first, let's go ahead and get the structure down. So game object, this game object that we just instantiated, dot transform dot position, and we're going to set it into its default location represented by this 3D vector. And we're about to figure out what these X and Y and Z should be, but this is the general structure. And what we're going to do here is to basically space them out evenly across the screen. So a lot of times you can just start putting something down, and once you see a drawing, you can then tweak it. So for here, we're going to say, let's start the first cube at the x coordinate of -512, right? We're going to basically say this thing's going to go from -512 to +512. It's going to be at a y coordinate height of 0, and it's not going to actually have any z depth. That's also 0. Default position will then just be this, and of course we're going to move x for each of the cubes so that it slides a bit towards the positive every time I have a new cube. That's the default position. Let's see, we're going to increment the x position for the next cube. So we can do x plus in some kind of increment. And for this, we can try to figure this out. This is calculate the increment, and we can do this as a function of the scale of the cube, basically the current size of the cube, right? We kind of want the cubes maybe kind of flush edge to edge, one cube after another. So maybe what we'll do here is do a float x increment equals whatever this prefab, the prefab cube dot transform, and it's a local, not Euler angles, local scale. Bit of autocomplete gone haywire here. So this is basically getting its local scale, getting its scale in the x direction. We use that right now just as a ballpark for our increment. And again, all of these numbers are adjustable to your liking. For now, I'm just going to get something working first. All right, so now what? So the next...
Should we give them a name?
Yeah, let's give it a name.
Yeah.
Give a name. And we can do this by saying go.name equals, and for this we can just say cube plus whatever the index of the cube is. So all these cubes will have a unique name. And I think we can
put them in an array.
Put them in an array. Let's see. Put into our cube array. So our cube array is the cubes. And sub I equals basically the reference to this new game object we just instantiated. Let's see, it's actually the cubes. And also we need to set this as a child of the waveform. Set as a child of this waveform. Right, so basically we're seeing this as a subcomponent of this entire thing we'll call the waveform. And we can do this with go.transform.parent and set that as this.transform. This is useful if you want to think about moving the entire waveform as a single entity without having to move all these individual 1024 cubes individually. Right, this is a really nice thing about hierarchical transformations. So we're just going to set this, hey, it's like I belong to this waveform. And then finally, we make sure that it's in our cubes array. All right. Anything else we need to do here? I think this is probably all we need for now. We may come back and add a few more things. But let's go ahead and get something drawing. And usually when we're doing this sort of thing, at least for me, Kangwoo, I feel like the most important thing is to just get something drawing at all. It doesn't have to be right? I mean, it's so. I
agree.
Yeah, we're going to try to do that. So what we're going to do here is to get back to that audio buffer, the audio array that we got from the microphone, and use that to position the cubes so that they respond to the sound. So here is a local reference to the time domain waveform. That's basically our sound wave. And we can say float. Let's call this WF for waveform. And we're going to get this from audio input, except we can't really do that, can we?
Can't.
So there's a couple ways. The reason we can't do that is because unless we actually have an instance of that to get, and we could actually get that instance from the audio source game object if we wanted to, right? The other way to do it is we can actually do a little bit of hack and make some of these things accessible without an instance of the audio input. So yeah, Kangwoo, which one should we do?
Let's hack it.
Let's hack it. Let's do it. So in this case, we want to access the audio data without an instance of the audio input. So we're back now in audio input. And here, what we were actually trying to access are basically the waveform, right? So I think I catch your drift, Kangwoo. I think you want us to add a static keyword here. This basically tells C# that this is basically like this is something accessible without an instance. It's effectively like a global variable that's been scoped within the class. So all you need to access this is the class name. So now if we go back to audio input, and now we can see the waveform is here. Yay. It's a good hack, at least for now. Hacks are good until they like come back and bite one in the butt. So as long as it doesn't bite us in the butt, it's good until then. But for now, I think this is probably good just to get something drawing once again. And here's the really important part is that remember that what we're getting here is the actual sound wave. There's going to be, in each one of these arrays, again, 1024 floating point, basically that many numbers. And each of the numbers is, you can think of that as the value of the sound wave at that particular point in time. And so we want to draw the fluctuation of this just from those values. So to do this, let's go ahead and position the cubes. We'll need a for loop. We're going to iterate through the entire array. And so here we're going to just do, we're going to iterate through you can do it either the waveform or you can do the cubes. Let's go ahead and iterate through the cubes and do it through the length of the whole cubes array. I'm going to set up the body of the for loop here. And what we're going to do here is to just transform it, in this case, up or down. In other words, really along the y-axis, keeping its x and z the same. So basically it's going to just go up and down depending on what that particular audio sample value is. Excuse me. So the cubes sub I dot transform dot local position. This is to emphasize that we're really doing this local transform, and especially since this is a child of another parent transform. So we're going to do this equals, I'm going to instantiate a new vector 3. And so what we really want here in the code is going to look, actually it's going to look a bit kludgy and verbose, but it actually is better than it might look. What we're going to do here is to basically say whatever the cube's current local position's x coordinate is, we're just going to keep that the same. So local keeps, well, I keep just hitting tab a bit too early there. Dot x, right? That's the x. The next thing is going to be the y. I'm just going to put this here as a placeholder. I'm going to come back and figure out what that is. And then similarly, we're not going to change anything about the z. Dot local position. Next time I'm going to hit the P letter first before I hit tab to autocomplete. Okay, so we'll have something like this. The question is what goes here? For this, we can say, what if we just hit whatever the waveform's value at that location really is? Right. Now keep in mind, the audio samples we're getting back from Unity are going to be in the range of -1 to 1. That's nominally the range. They're not supposed to go beyond that range. So given the scale of what we have, we will kind of have to, we really have to scale this up in order for us to be visible, right? But I guess we can, so for now, we can just, let's actually go ahead and run this before scaling it and see what happens.
Yeah.
So we're going to go back to Unity.
And attach the script. Oh, we should create an empty game object for
that's
our
right.
waveform.
We actually need a game object to attach this to. And for this one, we're going to just reuse the name waveform. Okay. And then we go ahead and do this.
Yep.
All right. Is that it?
Yeah. Let's see.
Let's see what happens.
See what happens.
How could this not work? Uh-oh. That's how it cannot work. So the variables, the cubes of waveform has not been assigned.
That's a very important part.
Yes, we actually haven't.
It's actually a very good error. So if you click on waveform in the hierarchy, and there's a game object that you have to attach to, which is the prefab we created. So we can drag and drop the cube, and Unity will be happy.
Very important, because they did not know what that was without us doing this. Okay.
Oh, nice.
So we already see something happening here. And
wobbling.
It's kind of wobbling. First of all, it's nice because now we see a whole line of cubes, and also as you hear me speak, you see somewhat that the cubes seems to be responding. So let's try that again.
Yeah.
Hey, what's up, cubes? There should be 1,024 of you. Okay. So this is interesting because it's responding to the sound. However, it doesn't look like a waveform so much, and certainly it's not a lot of. It just doesn't look that interesting. Here's where we're going to go back to do the scaling. I don't know. What's a good number, Kung-Lu?
Let's do like 100.
100.
Yes.
Okay, let's see what happens if we do 100 and we go back here. And let's run this. In fact, we're going to maximize this on play. Check.
Woo.
It's a little better. And we can also see the all the cubes at play. I'm going to do this so you can see it from both the scene view and the game view.
Wow.
Okay. So that's another step forward.
But I think the camera is a little bit zoomed in, so should we change the position of the camera so we can see the entire waveform?
Yes, let's do it. Looks like we have everything there, but just doesn't. It looks like we're not viewing it in the right way, right? Right. So how do we do this?
So you can do it by script, or you can easily do it by clicking on the main camera and changing the Z position, which is the depth. Okay. Or you can change field of view. It's your choice, but for now, we'll just change the Z axis to, let's say, negative 450.
450. That sounds like a great number. Let's do that.
Hopefully it covers.
Hey, check that out.
Ooh. Maybe we can zoom in a little bit. Maybe negative.
Let's actually play with this
here. Yeah, and you can remember the number.
So that looks pretty good.
That looks good.
So about 370, negative 370. So that is our new camera Z location. And we went out of play mode and go ahead and change this so now that this will stick around.
Saved. Yep.
Can
we see it again?
Yeah, let's do it. So maximize on play. Check. Oh, it's not too bad. Except the aspect ratio have changed since I maximized on play. Let me do without that. It's because this aspect ratio is just wider. Okay. Now we have a really important step in our audio visualizer. We have drawn something visually that corresponds to the audio and is responsive in an interactive manner. Right. So, great. What's next?
So let's do the spectrum.
Let's do it. So this will be quite similar to the waveform, but we'll be using, instead of the waveform data, we're going to use the spectrum data. We're going to also treat the rendering a little differently, but it's the same concept, right? So I'm going to go into script, and let's go ahead and create a new C# script. Let's call this spectrum. All right. And in the spectrum, let's do something similar. And for this one, I'm going to just go ahead and replicate some of the code we've already seen and call out some of the differences. So since we've already gone through these, we're going to go a little faster through just putting this code in here. But it's good to go through these again so we can kind of refresh as to what we've done. Again, we need a prefab reference, public game object, and this is going to be the PF cube. We're going to need an array of cubes, and I'm going to do public game object, and the cubes. And again, these are the spectrum cubes, and the only difference here, instead of 1024, remember we're going to use exactly half of that. And in start, here's our default positions in X, Y, and Z for each cube before we actually get any signal. And again, we're going to use the same scaling, negative 512. We're going to kind of have it go across the same width across the screen in the X direction. Z and Y are 0. We're going to compute an increment of how to change the X from cube to cube. And this one we're going to do a little differently, slightly differently, because in this case, remember, we have exactly half of the cubes as we do before. So our increment will need to account for that. So in this case, we're going to say, hey, X increment is the PF's cubes transform. I can't type. Dot local scale dot x, but times 2 to compensate for this factor of 2 difference in the number of cubes. And next, we're going to place the cubes initially. Go ahead, good old trusty for loop there. I less than the cubes dot length I plus plus, and then we can do the instantiate again. So game object go equals instantiate the PF cube. We're going to transform it. This is our initial transform. Go dot transform dot position equals new vector 3 x, y, and z. We're going to increment the x for the next cube, x plus equals x increment. We are going to actually, we're going to do another kind of transform here, which is to make it a little wider. Again, we're going to make the cube twice as wide, again, to account for this factor of 2 difference. We're going to do this by changing its local scale. So scale it to be 2x wider, go dot transform dot local scale dot equals new vector 3, apologies for that, 201. What else we need to do? Let's give it a name. For this one, this is part of the spectrum. One of the terms we use for this is a spectral bin. So we're going to say bin and then that particular number, the index of the bin. We're going to set this as a child of the parent of this spectrum. And so we're going to go dot transform dot parent equals this and dot transform. Finally, we're going to put into the array. So the cubes sub I is assigned the reference of go. All right, so I think that's our start.
Yeah.
And again, let's do the easy thing first and get something drawing. That's a pretty good rule of thumb for doing really any kind of like graphics programming, just to get something drawing and then you can fix it. Make it work first, make it right afterward. So we're going to have a local reference, this time to the spectrum, the frequency spectrum of the sound. So here is float, call this spectrum, equals, remember we're going to do the same thing we did here, except now we need to go back to audio input and similarly do our little hack.
Make it static.
Make it static. So now we can access the spectrum, this particular array, directly using the class name here. So audio input, the spectrum. Okay. Now the question is, well, what should we do to actually draw this? So let's go ahead and do let's the first order approach. Maybe let's just do what we did last time. Except we probably don't want to move this, but instead let's stretch it. Let's stretch the cube to the value of the spectrum. So let's go ahead and we'll need our trusty for loop to go through all the cubes again. And then let's see, for each cube, we're just going to change its transform. And the transform we're changing is none other than local scale. Or again, we're going to transform it in the y direction. So we're going to give it a new vector 3. And again, we're going to keep x and z the same, so the cube sub I. dot transform dot local scale. Never gonna actually get the autocomplete correctly. Dot x. Again, kind of this y thing we're gonna have to deal with in a moment. And then the cubes sub I dot transform dot local scale. And also we need another parentheses. No, actually I don't. Okay, so what do we put here as the y? In fact, I'll just call it y, and we can even figure the y out for each cube. We can say float y is, well, we know that we're going to have to use the spectrum somehow, so that's involved. But here's a spoiler alert. This number for like an audio signal that we're going to transform it through the FFT is likely to be really small, like 0.000 something, right? So we will need a pretty large scaling. And by the way, the range of this is going to be something that is going to be non-negative, because this is what we're really dealing with here is the magnitude spectrum. That's kind of the strength of the signal at a particular frequency. So with that, what we can do here is, I don't know, what's a good number here?
How about 600?
600, let's do it. If we do 600, let's see how this looks. Let's get something drawn first, and then we'll go from there. It's not liking this. Oh, it's because I forgot a dot length here. All right, looks like no more red lines under this code. Let's try it.
See what happens.
Oh, we need to do the similar thing here.
Yep.
So we need to create a new game object, spectrum, and let's see, we need to attach this to that. So attach our script to the game object.
Yep.
And
notice how spectrum's position is at negative 370 for the z-axis. So I would do a reset. So,
oh yes, I keep forgetting to do that. It's a good, really good.
It's next to transform. Yeah. So always reset after.
Always reset. So here, the only thing we need now is to connect the cube into the prefab into that field. Well, what will happen? Let's find out. Something has happened. We actually see the waveform and a little bit of the spectrum overlaid on top of one another. So we need to fix that. And it's also really hard to talk with like a slightly delayed version of yourself talking back at yourself. So I apologize for that. So in order to have them not overlaid on top of one another, we're going to have to move them. So here's where we actually want to go ahead and position both the waveform and the spectrum in kind of the global layout, right? So let's see. So in a way, this is based off of the SoundPeak S&D PEEK audio visualizer. So we can kind of use a similar type of a layout for that, in which case, let's go ahead and do the waveform, and let's move the waveform up a bit, and then we're going to move the spectrum down a bit.
Sounds good.
So for the waveform, we're going to be like position this, whereas in this dot transform dot position, and again give it a new vector. We don't want to move its x location. We do want to move it up. What do you think, Kangwoo? What's a good number there?
By about 100.
How about 100? Let's do it. This dot transform dot position dot z. We don't want to move that. We're going to keep that as it is. We're going to go ahead and copy this line of code, and we're going to go to spectrum and do something similar, except I'm going to guess, are we doing a negative 100 here?
Sure.
So however we move that up, we're going to move this lower so that it's symmetrical above about the middle of the screen. Okay, let's now try this again. This is exciting. All right. We now have a waveform on top, and we see a spectrum here. My lips are really dry right now. Sorry for the horrible whistling. But what we can already see here is that we could do a little bit more to making the spectrum a little bit more readily visible. You know, one thing we can do is I think the 600 is pretty good. We can either increase that, but there's another bad idea that we could try. And this is the part where, you know, really feel free to play with these things, right? There's no right way. Kangwoo and I have just been trying numbers. And I think for you, you know, whatever number I think looks right to you, that might be the better number to use. Or in this case, we're not even going to use a simple scaling. We're going to take the square root of the spectrum. And in a way, we're going to make this, we're in a way kind of compressing the value a bit so that the softer values actually, because these values are so small, by taking their square root, we're actually going to end up with a bigger number in a nonlinear kind of a way. So if we do, is it math.sqrt?
Mathf.
Oh, mathf for floating point.
Yep.
.sqrt.
SQRT.
And then I'm going to put the spectrum in here and still multiply that by 600. Now with just this one change, let's go back and see if we notice a difference.
Ooh.
All right. So we actually see a kind of a more robust spectrum on the bottom, and without adding a lot of extra, you know, kind of noise and whatnot to it. So we'll call this, you know, this is not bad. And so actually we are almost done. There are a few more cosmetic things that we could do, and it's fun to do that. So let's go ahead and do that. But you can kind of see this is most of our steps, right? So
Yeah.
let's see. What can we do, Kangwoo? What would be a...
Should we make it so that the spectrum starts at 0 and instead of scaling both up and down?
Right. So if we notice kind of the spectrum here, this is symmetrical about the center line. So the idea here is we want to make these more like a kind of almost like histogram bars that go to the top. This is kind of could be a kind of a typical frequency analyzer you find in software, or back in the old day when you had like a stereo system and that had like spectrum display. You often see these colored bars go up in a physical, like an LCD display on there too. So whatever the case, let's display this information a little differently. So how are we going to do that, Kangwoo?
We can move the position of the cubes.
Right. So here we are already using this Y to change basically the height of each cube. But then we can use this, really use it in the same information to move it so you always align the bottom of the cube to some set position, right? All right, so that means since we changed local scale here, I bet we just have to change something about local position.
Local position.
So here we're going to be careful to make sure we don't actually set scale as position. that would result in some interesting artifacts. This is the blessing the curse of copy and paste. It's really fast sometimes, but sometimes if you just forget to change local scale to local position in one place, you're gonna get some crazy results. So actually it turns out that, if the thing is, a certain height, right, to really align its bottom, we just need to move it up by half of that.
Right.
So just do y over 2. And if we do this, and by the way, at this point, we are just really changing things to really design out the visuals. And at this point, it's actually really it's highly encouraged that as soon as you make a change that you think could change something, don't wait. Go ahead and run this thing and see how it looks, right? And this is actually both really kind of satisfying if it works. Hey, in this case, it actually worked. And also,
Cool.
if something didn't work and you tried it soon, it's really probably in the code you just changed. So you don't write 50 lines of code and then run and be like, well, that didn't work. What part is wrong? So I think I would say just as a good rule of thumb, definitely run code often.
Yeah.
Let's see. Okay, well, we align the bottom of these cubes. What else can we do?
Should we change the color for each?
Yeah, let's do it. So right now we have this. What are the default colors for this cube?
Yeah.
And
it's I think with the ambient light and the directional light that's reflecting off of the cubes, it's kind of looking brownish gray.
Yeah, some brown. I mean, it's a fine color, but it's we want something that really pops against this black background. Also, as Kangwoo said, the lighting is actually in effect because these are 3D objects. So we want to kind of be more intentional about, trying out different colors. And of course, ultimately, the color's up to your preference. This is one of those things that's just fun to play with. But here's how you would actually do it. There's a couple of ways, right? And I believe we're going to try to do this in code.
Yeah, so you can actually change the color of the material used for a prefab. But since we use the same cube for both waveform and the spectrum, we might as well as do it in code. So we can have more flexibility in changing the parameter of the color. We can even attach the waveform data into color, and it will lead interesting results. But for now, we'll just have different colors for waveform and the spectrum.
Sounds good. So in essence, we're doing this because we could have actually just set a color onto the prefab itself. But since we're reusing this and we might want different colors for the spectrum and the waveform, this is actually, I think this is the easier way to go to color them differently.
I agree.
So here's going to do some color material. So we're back in waveform in the code in start where we're allocating these cubes. And you can kind of put this really anywhere in here, but we're going to go ahead and set the color to the material associated with this game object. And so I'm going to do go.get component render burr dot set color.
Set color, yeah.
And this. And basically here we're basically naming the field we're actually changing, correct?
One thing, in 3D, you can use _color, but in Universal Render Pipeline, URP, you have to use _base color with capital B.
Oh God, no. All right, base colors. That I was just gonna be like, every time I have to actually use a string to denote a field, I'm just like, what if I type it? I'm scared. I'm like, what if I type this wrong? And there's no type checking on the contents of the string, right? So
it's always scary.
It's a little scary. So this is a key thing because oh boy. Okay, cool. It's good to know. And then here what we need is then just a new color, and basically an RGB value. Do you have one in mind, Kangwoo?
It's a good color. Should we try green?
Green, sure. Let's try green. So what flavor of green might we try? So green is going to just have a lot of the G component. We could do it 0, 1, 0.
Yeah.
That's a green. That's this just green, purely green in an RGB sense. And again, now that we made this change that we think should affect the graphics, let's see what happens. Does it actually make it green? Hey, there it is.
It's very green.
It's very green. Not bad. So maybe we can keep that. And shall we do a similar thing for the spectrum?
Mm-hmm.
So I'm going to copy this and go to the same place in the start function for spectrum and set its base color to something.
Let's do blue.
Blue. So instead of green being 1, I'm going to put blue as to 1. Let's see what this looks like. And we'll wait for Unity to think about it. And then we're going to go ahead and start this. There is blue.
Yay.
Yeah.
Oh, wow.
I
can see the harmonics.
Yeah. I like the blue, but it seems like it doesn't pop as much as the green.
Mm-hmm.
So maybe what we can do here is to make it just a bit brighter. What if we go 0.5, 0.51, and to give it a bit more of the red and the green component here, but since those are an equal amount, this is still going to keep the greenness, but it's going to make it lighter. Uh-oh, except I broke it. So these needs to be actually denoted as single precision floating points rather than, or else going to interpret them as double precision. Let's go over here and hit play. All right. More of a pastel.
More pastel. Can we also make green a little bit pastel?
Yeah, let's do it.
I love pastel.
Me too. And again, this is like, there's no right answers here. There are no wrong answers here. So whatever color strikes your fancy would be a good color. Only consideration might be a functional one. So, how well can a viewer actually discern the waveform and the spectrum? But other than that, it's well, I guess we'll get to figure out the form and function balance here. Ooh, I like the pastel green.
Yeah.
Very cool. So let's actually. I think we've actually done everything we've set out to do. But before we wrap up, let's view this one more time, but maximized on play, and see this in its near full screen glory here. I'm actually hearing some audio artifacts when I'm doing that.
Really?
And I don't know if it's the recording I'm doing or whatnot, but yeah. But it looks pretty good. And so I think we've more or less done what we've set out to do, which is to make a basic starting point interactive audio visualizer by getting audio from Unity, from the microphone, and then drawing it both in terms of its time domain, waveform, as well as some plot of its frequency content for a particular audio buffer. So, at this point, we will offer some suggestions, I guess, as what else one could do with this, because this is just a very a starting point. What do you think, Kung-Woo? What are some?
Well, I think this is where the fun really begins, right? So
absolutely,
you have the parameters you can play around with, and really the point where you can go super crazy.
Right. Anything that's like a number in here might be a good place to start adjusting, right? Instead of a square root, change it to something else. And I think just asking, like, what if we did that, right? Or use more cubes, or don't use cubes at all. Use a line, use spheres, use I don't know, models of teapots. So there
Yeah.
are a lot of things you could do. And in fact, if you were to look at something like SoundPeak, and again, we can throw a lot of the URLs and things in the description below this video. SoundPeak actually draws a history of the spectrum, so that you not only see the current one, but you see like echoes of the last like 64 spectra. And that gives you a sense of how sound is changing over time in the frequency domain. And of course, the entire design, the entire visual design of this can be completely different. Why a line? Why a straight line? Why not like a circle? Why not a light bulb or the shape of an ice cream cone? Why can't this look like someone's head on fire as they're listening to music, right? There's a lot of visual design that can go into this, but I think this is really about, now that you have the audio hooked up to the graphics, I love what you said, Kangwoo. This is where the fun really begins.
Yeah.
And I think in a future tutorial, we'll talk about something that was not needed in this particular tutorial, and that is actually integrating Unity with Chuck, which is a music programming language you can use to programmatically generate sound. And it's a powerful language for generating real-time sound that through Unity, which is the integration of the two, and that exists as an asset in the Unity Asset Store, you can actually do real-time audio synthesis and music synthesis in a way that's tightly integrated with Unity, right? We could have done this in Unity if we wanted to, and actually be able to have the spectrum analyze and visualize whatever is being played out of Chuck, or out of any program that you write in Chuck. So I think that's going to be for another tutorial potentially. But yeah, there's no, there's really no limit as to where you could go from here. So yeah, anything else, Kangwoo, to add before we wrap up?
Yeah, I mean, if you make cool projects with audio visualization in Unity, please share it on YouTube and possibly email us the link.
Or share them in the comments below if you're watching this on YouTube. All right, so thanks for checking out this Artful Design TV coding tutorial. If you found this useful, please like this video and subscribe for more content like this, including more coding tutorials for audio, visual, music, interaction, VR, and more. So until next time, this is Kangwoo and Ge signing off.
Bye-bye.